In this lesson, we're going to apply your knowledge of partial derivatives to find the extrema and critical points of a three-dimensional space. So we know from when you took calculus 1 or 2 from A, B, and B, C that you can find the relative extrema by setting the derivative equal to 0. You get the critical points, and then you can test whether or not it's higher or lower than the values around it. But when we have a multivariable equation here, you have to set the partial derivative of x equal to 0 and the partial derivative of y equal to 0, and that gives you the x and y coordinate for which this point is a critical point. So if you look at the function f of x, y, and it is greater than or equal to f of some critical point for any other x, y, then your critical point x0, y0 is going to be a relative minimum. If f of x, y is smaller than your critical point f of x0, y0 for any other x, y, then that makes your critical point x0, y0 a relative maximum. So we're going to get our critical points by setting the partial derivative with respect to x equal to 0 and the partial derivative with respect to y equal to 0. And to remind you, we're going to label our critical points in definitions as x0, y0. So let's take a look at an example on the next page. I'm not going to show you what the graph looks like yet. I want to find the critical points, and then I'll import the graph and show you what it looks like. All right, so we're going to determine the relative extrema of f of x, y equals 2x squared plus y squared plus 8x minus 6y plus 20. So first thing I need to do is find the critical points. And to do that, I'm going to set the partial derivatives equal to 0. So my partial derivative with respect to x is going to be 4x plus 8. And my partial derivative with respect to y is going to be 2y minus 6. And so I can set each of these equal to 0, and I get x is negative 2 and y equals 3. So the point negative 2, 3 is a critical point. And so I need to see how this critical point compares to every other xy value around it. And so I'm going to take the function f of xy, and I'm going to test some points around negative 2, 3. So I've got my function f of xy equals 2x squared plus y squared plus 8x minus 6y plus 20. And I first want to see what the z value is when I plug in negative 2, 3. So remember, this is the same thing as giving you the z coordinate, but I'm going to figure out what f of negative 2, 3 equals first. So 2 times negative 2 squared plus 3 squared plus 8 times negative 2 minus 6 times 3 plus 20. You can evaluate that, and you get f of negative 2, 3 equals 3. And so we need to see how other values of x compare to this z value, other values of x and y, how this compares to this z value. So I can pick any other points. Maybe pick something kind of close, maybe f of negative 3, 3 even. So this is going to be 2 times negative 3 squared plus 3 squared plus 8 times negative 3 minus 6 times 3. So we've got 18 plus 9 minus 24, forgot the plus 20, minus 18 plus 20. And we can do a little bit of mental math. 27 minus 24 is 3. 3 minus 18 is negative 15. Negative 15 plus 20 is 5. So that's bigger than 3. And I can pick any other value, maybe pick something to the right. So I can also test f of 1, 1, or even 0, 0 if I wanted to. I'll test 1, 0. 2 times 1 squared plus 0 squared plus 8 times 1 minus 6 times 0 plus 20. And when I do that, I get 2 plus 8 plus 20, which is 30. So f of xy, for any xy, is greater than or equal to our critical point. So that means that the critical point, -2, 3, is a relative minimum at z equals 3. Now here's what the graph of this surface looks like. It was an elliptical shape or a parabolic shape that was flipped up into somewhat of like a cone type bowl shape. And you can see that at the point -2, 3, 3, that's where your minimum is. So the next example we're going to do is looking at what a relative maximum is. So in this example, it's a little more complex. It looks like we're probably going to have some undefined terms here. We're going to find the relative extrema of f of xy equals 1 minus x squared plus y squared to the 1/3 power. So I'm going to start by finding some possible critical points by taking the partial derivatives with respect to x and y. So my partial derivative with respect to x is going to require the chain rule. So the derivative of the outside is -1/3 x squared plus y squared to the -2/3 times the derivative of the inside with respect to x, which is 2x. So now I have, if I simplify this a little bit, I have -2x on the top over 3 times x squared plus y squared to the 2/3 on the bottom. The partial derivative with respect to y is going to be very similar. The derivative of the outside is -1/3 x squared plus y squared to the -2/3 times the derivative of the inside with respect to y, which is 2y. And that simplifies to -2y over 3 times x squared plus y squared to the 2/3. Now if I wanted to set these equal to 0, I get x equals 0 and y equals 0. It's also undefined when both x and y equals 0. So I think it's safe to say that we have a critical point at 0, 0. And so I'm going to see what the function evaluated at 0, 0 equals. Because remember, f of xy is the same thing as saying z equals. So we can find that z value, the height value. So I'm going to plug in 0, 0. F of 0, 0 is 1 minus 0 plus 0 to the 1/3, which is just 1. And I want to see how other values around it compare to 1. So I can plug in something easy, maybe 1, because it's a 1/3 root. We want to pick things that are going to have a nice root. F of 1, 1 is 1 minus 1 squared plus 1 squared to the 1/3, which is 1 minus 2 to the 1/3, so cubed root of 2, which we know is going to be less than 1. I can plug in something else, maybe -2, -2. So 1 minus -2 squared is 4, -2 squared is 4 to the 1/3, so 1 minus 8 to the 1/3, which is 1 minus 2, which is -1. Well, -1 is also less than 1. So that means that f of xy for any xy other than 0, 0 is less than or equal to our critical point, which means that 0, 0, 1 is a relative maximum. Or you could also word it the way we did in the previous example. 0, 0 is a relative max at z equals 1. And so that's how you find critical points and the relative maximum or minimum for one of these problems. While we were finding the critical points and seeing if there's a relative max or a min, you were probably thinking back to your previous calculus classes, well, what about the second derivative test? Well, there does exist a second derivative test for multivariable problems, and we call that the second partials test. The second partials test is not as easy as the second derivative test that we did for one variable calculus, because sometimes what you think is a relative minimum or a relative maximum in your when you do the first derivatives or the first partial derivatives, it can be misleading. Sometimes it's neither a relative max nor a relative min. And so when it's neither of those, but it still has some sort of difference, then we call that a saddle point. Now that could be thought of analogous to a inflection point when you were doing one variable calculus. So a saddle point is where the surface literally looks like a saddle. That's why they call it a saddle point. And so there's some rules to tell if it's a relative max, a relative min, or a saddle point. And those rules you kind of need to memorize. I'm going to write them here. The first thing we have to do is find the partial derivatives. So the test has a few steps here. We're first going to find where f of x equals 0 and where f of y equals 0, the two partial derivatives. And that'll give us some point AB. It gives the critical point AB. Then we're going to consider a new variable. So D is going to be the second partial of XX of AB times the second partial YY times AB of AB, minus the mixed partial FXY of AB squared. Now, if that's a complicated formula, you could think of D as a determinant of all the possible partial derivatives. So D, and this is why we call it D, it's the determinant of all of the possible partials. So, for example, fxx of AB, fxy of AB, f of yx AB, and fyy of AB. So these are all the possible partials. Now the reason that the formula above doesn't quite look the same is because fyx will give you the same value as fxy, which we proved in an earlier section when we first started doing partial derivatives. So this formula that I wrote above is just the determinant of all the possible partials. And so there's 4 rules, and that will determine whether or not you have a relative max, a relative min, a saddle point, or an inconclusive value. So the first rule, if D is greater than 0 and the second partial of x at that point AB is greater than 0, then you have a relative min. If D is greater than 0 and the second partial of x is less than 0, then you're going to have a relative maximum. The third rule, if D is less than 0, then that means you have a saddle point at AB. And rule 4, if D equals 0, your test is inconclusive. So we've got 4 different ways that D could turn out. D could be positive, and the second partial of x is positive. That means you've got a relative minimum. You could have D positive and the second partials of x less than 0, and that means you have a relative maximum. And then if D is less than 0, then that means that you have a saddle point. If D equals 0, then it's an inconclusive test. So let's do an example where we try to figure out if it's a relative max, a relative min, or if it's a saddle point. In this example, we're going to find the relative extrema of the function f of xy equals negative x cubed plus 4xy minus 2y squared plus 1. So the first thing I need to do is figure out a critical point or critical points. And I'm going to do that by setting the partial derivatives equal to 0. So the partial derivative of x with respect to x is negative 3x squared plus 4y, and the partial derivative with respect to y is going to be 4x minus 4y minus 4y. This sets up a system of equations because they're both going to be equal to 0. So I know from the second equation 4x equals 4y, which means that x has to equal y. So now I'm going to substitute x in for y into the second equation. Negative 3x squared plus 4x equals 0. I can factor out an x, so I have negative 3x plus 4 equals 0. So that means x equals 0 and x equals 4/3. So I have 2 critical points. One is at 0, 0, and one is at 4/3, 4/3. Now I can find my second partials so that I can figure out my D value. So my second partials here, I'm going to have fxx, which is going to be negative 6x, and fyy is going to be negative 4. And then I also need to find fxy, which I'm going to show my work how I get. So fxy means I take the partial of x and then take that function and take the partial of y. So first I'm going to do the partial of x, which is negative 3x squared plus 4y, and then I'll find the partial with respect to y of that function, and I get 4. So I've got my 3 main partials, because remember, f of xy is the same as fyx, so both of those are 4. So I can find my D value. D is my f of xx at my critical value times fyy at my critical value minus these two multiplied together. So I can just write one of them, fxy at AB squared. And so now I can plug in, I'm gonna use AB equals 0, 0 first. And so I can plug those values in. So I'm going to have negative 6 times 0 times negative 4 minus 4 squared. And I end up with negative 16, which is less than 0. So D is less than 0, which means that there's a saddle point at 0, 0. So there's a saddle point at 0, 0. And I can plug 0, 0 back into the original equation, and that'll tell me the y value at which you have a saddle point. So if I plug in f of 0, 0, I get negative 0 cubed plus 4 times 0 times 0 minus 2 times 0 squared plus 1, which equals 1. And so I can actually amend this to have all three values. At 0, 0, 1, there's a saddle point. That's my first answer. Now I need to check the critical value. AB equals 4/3, 4/3. And so I'm going to plug those values into my D equation. So D equals my second partials of x, so negative 6 times 4/3 times negative 4 minus 4 squared. When I simplify this, I end up with negative 8 times negative 4 minus 16, which is 32 minus 16, which equals 16. That's greater than 0. That means I'm going to have either a max or a min, since it's greater than 0. And so now I need to check which one it is. So I need to plug it into my second partials of x. So since D was greater than 0, I need to figure out what my second partials of x at this point equals. At 4/3, 4/3 equals. So I'm going to plug that into the negative 6x. Remember, f, my second partials of x, at 4/3, 4/3 is going to be negative 6 times 4/3, which is a negative 8. Since that's less than 0, that means I have a relative maximum. So fxx at 4/3, 4/3 is less than 0, so I have a relative maximum at 4/3, 4/3, and I'm going to plug 4/3 into my original equation. Negative 4/3 cubed plus 4 times 4/3 times 4/3 minus 2 times 4/3 squared plus 1. And when I plug that in, I get 59/27. I used my calculator for that. Obviously, this is a long process, and you just have to remember the rule. Once you remember the rule, you just have to grind out the work here. So this sums up our derivatives. I am going to do a video of a couple application problems, and then we're going to move on to integrals. That's our next unit. So do some practice problems of this so you can be ready to ask me questions.